This video is for AP Statistics Chapter 4, and in this video we're going to cover nonlinear data. So before we've been doing stuff with linear data and more of a linear model, and sometimes that's not going to be a good fit for the data because that's not the relationship. And so in this video we're going to cover what to do when your relationship is nonlinear. So there's two main kinds of nonlinear relationships that you cover in AP Statistics, and the first is what's called a power function, and this is going to be your y equals ax to the b. And usually when you have a power function, they're going to give you a hint as to what the power is going to be. They're not going to expect you to know what it is right off the bat given the data. So they might say like, oh, the relationship, maybe there's a square relationship or a cubic relationship. And then your exponential function, this is the second type, and this is going to be a y equals a b to the x. And so kind of like a subtle difference, just the b and the x are switched in both models. And so then there's also something called linear growth versus exponential growth. And linear growth is when you add a fixed increment in equal time. So a line, if you look at the slope, that's a fixed increment in equal time. So for each, if the slope is 5 halves, then for each increase in x, it's going to go up 5 halves. And then we also have something called exponential growth. So this is when it's multiplied by a fixed number greater than 1 in each equal time period. So that's when you're going to have something like this. That's making it increase more rapidly. And so here we get into what's called exponential growth and decay. And so for one of the first things to know about exponential growth and decay is that there's a common ratio. And this is, so say we have a list of y values that's 3, 10, 20. If we wanted to figure out, if we thought that this was exponential, it would have a common ratio, and how we would figure this out is that we would take one y value and divide it by a different y value. So what we would do is we would do how you figure it out is you take y to the n and you divide it by y n minus 1. So here this is our first, second, and third y values. And so what we would do is we would take y3 and then we would divide by y2. So that would be equals 20 over 10 equals 2. So if, say, instead of a 3 here, let's say it was actually a 5, then it would be y2 over y1, and that's going to be 10 over 5 equals 2. So then these would both have the same common ratio of 2, and we could say, oh, maybe this is exponential because it has the same common ratio. And if all of the y values have a common ratio, when you do yn divided by yn minus 1, then it's exponential. So yeah, you're dividing numbers of sequential y values. And so the next step when you figure out is something a power function or an exponential function is you're going to want to do a logarithmic transformation to kind of get the same linear relationship. You're always kind of, even if you don't start off with a linear relationship, you're going to get to a point where you can get it so that you can do a least squares regression line or something similar to that. So what you do if it's a exponential model is you're just going to take the log of y. So if it's exponential, you're going to do log y equals a times bx, And if it's a power model, you're going to take the log of both sides, and you're going to end up with log y equals a times b log x. And so here's just a little chart to show that if this was a good fit for an exponential model, and we took the log of y and we set it up, this would be our linear regression line right there. And so then once you take the log and you figure out what your kind of linear line is going to look like, then you're going to want to create a residual plot. And the residual, as we've discussed before, is y minus y hat, so it's your observed value, and then you're going to subtract your predicted value. So when you figure out the residual plots with exponential data, is it's going to be you're going to plot the residual against the explanatory variable. So plot. And so this is when you have your equation log y hat equals a times bx. When you calculate the residuals for everything, then you're going to plot that against the explanatory variable. So it'll look like x residual. And so then there's 3 requirements for any of these nonlinear models. The first requirement is that you have a strong R value. And as we've learned before in chapter 3, an R value is just showing correlation between data. So it doesn't mean anything as to whether it's linear, nonlinear. It's just showing that there's a pattern where, say, for example, if it was a direct relationship, with every increase in x, there's going to be a similar increase in y. And then also, you're going to want to make sure that your transformed data is linear. And your transformed data can either be from an exponential model or it can be from a power model. And then also, the third one is you're going to want to make sure that you have a random residual chart when you do plot the residual versus the x explanatory variable. So there you have it. That's nonlinear data.